Hello, Martin and Hamna.
Yeah, you can continue.
Okay, so in the last class, we discussed the properties of magnetic field line. Okay, we have discussed that. Properties of magnetic field line. So today we will discuss the magnetic effect of current. Okay. So let me show you where we have discussed that. Just a minute. So we discussed that. Martin, have we discussed the properties of magnetic field line? I think I have discussed. And I have given the homework also. Yeah.
Yes.
Okay, so basically today we will discuss what I am going to discuss today. The magnetic effect of current we will discuss.
Yes, sir.
Magnetic effect of current we will discuss. Okay, so so magnetic effect of current, with the help of current, if there is a magnetism, that is known as the magnetic effect of current. So magnetic effect of current means a current flowing in a wire produces the magnetic field around it. A current flowing in a wire produces the magnetic field around it, and it is the magnetic effect of current. Basically, if there is a wire, there will be a magnetic field around that wire. Okay, we will see that, and that is known as the magnetic effect of current. So we can say that current is what? Current is basically the electricity, and magnetic field is what? Magnetism. So it means that electricity produces magnetism. Electric motor, electric generator, telephone, radio, all utilizes the magnetic effect of, current. Okay, this is what the magnetic effect of current. So now there will be one experiment. Okay, there will be one experiment. With the help of that, we can observe the magnetic effect of current. We can observe the magnetic effect of current. Okay, so this is the experiment. This is the compass, magnetic compass. This is the magnetic compass, and basically what is happening here, this is the wire. Okay, A and B is a wire. A and B is a wire, and this wire is connected with, this is a battery, this is a battery, and this is the switch. This is the battery and this is a switch. This time the switch is open, and here a magnetic compass is placed. Here a magnetic compass is placed, and this magnetic compass is along north-south direction. North-south, if the magnetic compass is along the north-south direction, means there is no deflection in the compass. If the compass will be deflected this way, it means there will be the magnetic field. Okay. So suppose you close this switch. When the switch will be closed, there will be the current flowing in this wire, and there is a deflection in the magnetic compass. So there is a deflection in the magnetic compass, and if there is a deflection in the magnetic compass shows that the magnetic field at a point. there is a deflection on the magnetic compass, means there is a magnetic field here, that is why this compass is getting deflected. Means due to that magnetic field, there is a magnetic force on the magnetic compass, that is why the magnetic compass is getting deflected. So with the help of current, you can see here is the magnetic field around it. So the deflection of the compass needle in the above experiment shows that an electric current produces the magnetic field around it. So this is proved. If you want, you can also do this experiment. Take one magnetic compass, take one wire, battery or switch, place the compass near the wire, close the switch, and you will get that the compass will deflect. And this deflection is the proof that there is a magnetic field there around the wire. If you will place this compass here also you will find some deflection in the compass. And deflection in the compass showing magnetic field, means magnetic due to the current in the wire, there is a magnetic field around it. So the deflection of the compass needle in the above experiment shows that electric current produces a magnetic field around it. Okay, so this is the experiment now, clear? So with the help of the electric current in the wire, there can be the magnetic field around it. Now we will see the magnetic field pattern or magnetic field line due to different types of wire, straight wire, circular wire. Magnetic field pattern means magnetic field lines. So magnetic field pattern, magnetic field line by different current carrying conductors or of different shapes. So first we will see the magnetic field lines due to a straight conductor or a straight wire carrying current. Secondly, we will see the magnetic field due to a circular loop or circular wire carrying current, and a solenoid. After that we will see a solenoid, and basically a solenoid is an electromagnet. We will discuss that. So magnetic, first of all, magnetic field pattern due to a straight current carrying wire. So basically in this figure this is a wire AB. This wire AB is connected with a battery. This is a switch. This is a closed switch, means the current is flowing in the wire. And if the current is flowing in the wire, I told you there will be the magnetic field around the wire. The shape of the magnetic field will be the concentric circles. Shape of the magnetic field will be the concentric circle. And you can plot these concentric circle with the help of the compass. So I am not going in that. Basically you should know the magnetic field around a wire will be the circular or magnetic field line around the wire due to the current, or you can say due to the current carrying wire, will be circular. So these are the magnetic field lines. Okay, these are the magnetic field lines. I am not talking about the direction, anti-clockwise or clockwise direction. I will tell you later. So in this, the current is in this direction, and the magnetic field lines are circular, concentric circles. So magnetic field pattern due to a straight current carrying wire are the concentric circles. So I have written here. So magnetic field lines around a straight conducting wire carrying current are concentric circles whose centers lie on the wire. Okay. Now it has been shown by the experiment that I told you in the last class that when you will go in your 12th class, if you have there the physics, so in the chapter magnetic effect of current, you will study Biot-Savart law, and in Biot-Savart law you will find some observation. Okay, you will find some observation that the current is directly proportional to the distance between the wire, and the current is directly the magnetic field is directly proportional to the current flowing in the wire. Basically different proportionals you will see there. But here it has been shown by the experiments that magnitude of the magnetic field produced by the straight current carrying wire at a given point is directly proportional to the current passing in the wire. Means more amount of current will pass in the wire, more will be the strength of magnetic field, more will be the strength of magnetic field around the wire. Okay. Inversely proportional to the distance of a point from the wire. For example, this is the current carrying wire. In this wire, the current is going in the upward direction, and this is a point P at a distance A. So you can say that the magnetic field inversely proportional to this distance. Means if you will increase the distance, suppose this is a point P. At point P, the magnetic field this time is suppose 5 Tesla. Now, if you will increase the distance to 2a, means if you will increase the distance, definitely the magnetic field will decrease. Okay. So when you will increase the distance, the magnetic field will decrease. At this point, the magnetic field will be something else. And if there is any other point, suppose this point is P dash. So magnetic field at point P is greater than P dash because the distance of P dash is greater. So that is why I am saying that magnetic field is inversely proportional to the distance between the point and the wire where you are calculating the magnetic field. And one more thing, this magnetic field due to a straight current carrying wire is directly proportional to the current flowing in the wire. More amount of current will flow in the wire, more will be the magnetic field at any point or around the wire. Okay, now we will talk about the direction. So basically, direction of magnetic field produced by the straight current carrying conductor of wire. So direction is given by Maxwell's right hand thumb rule. Now, what is right hand thumb rule? What is right hand thumb rule? See this wire. In this wire, the current is in the upward direction. So what you should do? Right hand. You will take your right hand. And you will hold the wire. Not actually, you will imagine that you are holding the wire, you are grasping the wire, but your thumb should be in the direction of the current. Suppose this is the wire. And in this wire the current is in the upward direction. So what I will do, thumb should be in the direction of the current, and imagine that you are holding this wire like this. So the sense of curling of your finger will give you the direction or will give you the pattern of the magnetic field line. So my fingers are curling in a circular pattern like this.
Left hand or right?
No, right hand, not left. Okay. Right hand, not left hand. Okay. So in this way you have to do. So you can see here in this figure, this is the right hand written here, like this. And if the current is in downward direction, so you will do like this. So in this direction, you will get the magnetic field. So this is the direction of the magnetic field. Okay. This is anti-clockwise. So if the current is in the upward direction, then you will get the anti-clockwise. Okay. And this is a straight wire, right hand thumb rule. Understanding the right hand thumb rule? I have written here.
Yes, sir. Yeah.
Imagine that you are grasping or holding the current carrying wire in your right hand. Imagine that you are grasping the current carrying wire in your right hand. Okay. No, you can see. Imagine that you are holding the current carrying wire in your right hand. This is your right hand. Okay. And imagine that you are holding this wire. Not actually holding, means imagine holding your wire. Your thumb should be in the direction of the current. Like this. And you are holding. The direction in which your finger will encircle, like this or like this. So this will decide the direction of the magnetic field. So if your fingers are going like this, means anti-clockwise, like this means clockwise. Okay. So imagine that you are holding the current carrying wire in your right hand so that your thumb points in the direction of the current. Okay. Then the direction in which your fingers encircle the wire will give the direction of the magnetic field lines around the wire. For example, current is in this direction, so direction of the current is in the upward direction. So what you will do? This is the wire. Okay, this is the wire, and current is going in upward direction. So what you will do? Like this. Imagine that you are holding the wire and your thumb should be in the direction of the current, and encircle your finger to hold the wire. So you are encircling your finger like this. So it is anti-clockwise. Now the current is in the downward direction. Okay. Now your thumb should be towards the thumb should be towards the direction of the current, and now hold the wire. Now simple thing I am telling you. First do your thumb towards the current. If current is upward, so do the current upward. Do the thumb upward, and then hold the wire. And direction in which your finger will encircle will give the direction of the magnetic field. Now current this time is in the downward direction. So do your thumb in the downward direction, right hand thumb, not left hand, and encircle like this. So you are getting this direction, and this direction is clockwise direction. This direction is the clockwise direction. So basically this is all about the straight wire. Now we will discuss for this circular wire, the pattern due to circular wire. So due to circular wire, this type of pattern you will get. Basically this is a circular wire. There is a circular wire, and this circular wire is connected with a battery, so that there will be the current in the circular wire, and due to the magnetic effect of current, there will be the magnetic field around the wire. So this type of pattern the circular wire will have. See this pattern. Okay. Here, this is the wire. Around the wire there are the circles, and now when you will move away from the wire, the radius of the circles will increase, and at the middle the magnetic field lines are a straight line. At the middle the magnetic field lines are the straight line. So basically these are the magnetic field lines. So basically these are the this is the magnetic field pattern you will get. This is the magnetic field pattern you will get. This type of magnetic field, okay, pattern you will get. These are the magnetic field lines, or you can say magnetic field pattern. So what is this? This is a circular wire loop connected with a battery, and with the help of this battery the current is flowing. Okay, this is the circular current. Basically current will, the wire is circular, so current will flow in the circular form like this. Okay, so the theory I have written already. A circular wire fixed to a thin cardboard T. So basically this is a cardboard T. T is the cardboard, thin cardboard. Why we have taken the cardboard? Because we want to show the pattern of the magnetic field lines. Okay, so a circular wire fixed to a thin cardboard. So basically this is a thin cardboard, this thin cardboard, and this is a circular wire somehow fixed with this cardboard. Magnetic field line near the wire are circular. So this is the wire. So near wire, the magnetic field lines are circular. Okay. As we move away, concentric circles become bigger. Now you can see these this will, when you will complete this now. So these will also be the circles. Okay, like this. Okay, when you will complete this. So these circles will become bigger. These are the concentric circles, and these will become bigger and bigger. Okay, you can see smaller circle, larger, then this is another, this is also a circle, and this is another larger circle, this is larger, so then larger. So magnetic field near the wire are circular. As we move away, concentric circles becomes bigger. Move away, move away, so concentric circles becomes bigger. Now at the center, this is the center. At the center of the loop, magnetic field lines are a straight line. C point M. So now see, here this is the straight magnetic field line at the center. This is what? This is the straight line, straight magnetic field line. Straight magnetic field line. Straight magnetic field. Magnetic field line. Now, strength of the magnetic field due to a circular wire. Basically, when you will go in your higher classes, so there will be a derivation, okay, that you will study for the circular wire, for the straight wire. With the help of the Biot-Savart law, you will calculate that. But right now, you have to learn only these things, okay? So that will be V is equal to mu naught upon 4I, MI by R, I think. NI by R will be the formula. The strength of the magnetic field produced by the circular loop depends upon the number of turns in the wire. How many turns are there in the wire? Okay. Circular wire, in circular wire, there can be number of turns, 1 turn, second, third, fourth. There can be the number of turns in the wire, in the circular wire. So the magnetic field strength around the wire will depend upon the number of turns in the wire. Secondly, current flowing in the wire. More will be the current flowing, more amount will be the current flowing, more amount will be the current flowing in the circular wire, more will be the strength of magnetic field around this wire. Number third, radius of the circular loop of the wire. Basically, it is inversely proportional to the radius. Okay, inversely proportional to the radius. More will be the radius of the wire, less will be the magnetic field. Okay, so here I am writing increasing radius. Increasing radius will decrease the magnetic field at a point, will decrease strength of magnetic field. So you should only keep in mind, basically, it is depending only on the radius. Okay, so there is no requirement of this. You should know it is depending on the radius. Decreasing or increasing is another thing. Okay, depending upon the radius. If you will change the radius, the magnetic field strength will change. So I will not go beyond your syllabus. Okay, will stick to your syllabus. Okay, now after that, this is another very easy topic. A current carrying circular loop or a wire behaves as a thin disc or a type of magnet. So basically, you can see here. So basically, this is a wire, circular wire. This is the circular wire. Circular coil, you can say, or wire, you can say. So if there is a current flowing in this wire, now, so this will behave as a magnet, and magnet having south and north pole, na? So now see, you are watching this face, the face you are watching, and see the direction of the current. If the direction of the current is clockwise, like this, so the phase that you are watching will behave as a south pole, and the phase which is behind will behave as a north pole. Okay. So the direction of the current in this phase of a circular wire is clockwise. So this phase of the current carrying wire will act as a south magnetic pole. If the current will be anti-clockwise, in this circular wire, the current is anti-clockwise, so it will behave as a north pole. The phase which is opposite to it will behave as a south pole. Now few questions are there. First take the screenshot, then we will do the question. all of you, Hamna, Martin, Sarah, please take the
Yes, sir.
screenshots. Please take the screenshots.
I took.
Okay, took. Martin, please take the screenshot.
Yeah, okay, sir.
Done? Martin completed?
No, I'm doing.
Okay, okay. So no, you have to take the screenshot. Do not write.
Okay, sir. I'm done.
Take the screenshot, and then when you will take the screenshot, arrange these screenshot. Then you should write, because we have to save the time. We do not have much time.
Yeah,
So
I took screenshots.
took.
Yeah.
Okay. So now take the screenshot of this. Took the screenshot.
Yes, sir.
Okay. So now, Martin, done.
Yeah, done.
Okay. So corresponding to this, na, the theory I have written here. Okay. So actually, what you should do, na, you should take the screenshot like this. Then it will be better. Okay. Now take the screenshot again.
So should we write this down?
Hmm.
Should we write this down?
Oh, actually, you can write this, but actually, we do not have much time. So that is why I'm saving time. You should took the screenshot. Then after taking the screenshot, if you want, then you can write, na. You will have the notes. Understanding what I want to say?
Sure. Okay.
Hmm. Means you are not okay. If you are not able to take the screenshot, then I will share you the notes.
Okay, sir.
Are you able to take the screenshots?
I already took some.
Okay, so then it's fine. Okay, now take this screenshot. Sarah, are you able to take the screenshots or not?
Yes, sir.
Okay. Done, Martin? Sarah?
Yes, sir.
Martin?
Yes, sir.
Martin, tell me if there is any problem. No problem. You can tell me if there is any problem in taking a screenshot. Are you fine with it?
Yeah, took, sir.
Okay. Just a minute. So this after this. Okay. Now take this screenshot. Okay. Now take this screenshot. Done, Sarah and Martin and Hamna?
Yes, sir.
Martin, done?
Yeah, took, sir.
Okay, now please take this screenshot. For revision, you should write this on your proper notes. You should have a copy of this class, tuition class. So
Yes, sir.
after that, you should write all these theory there. I am doing this because I want to save time. Means if you will write, then it will take 20 minutes or it may be take 25 to 30 minutes and we will have a class of 1 hour in 1 week. So how can we finish the syllabus? That is the problem, no?
Yeah.
Otherwise, I always want that the students should write their notes by yourself. Done? Sarah, Martin and Hamna?
Yes, sir.
Yeah, sir.
Oh, good. Okay, now take this screenshot.
Done.
Hamna, please, you should also take these screenshots. Done? Martin and Hamna and Sarah?
Yes,
Yeah,
sir.
done, sir.
Oh. Scroll down. Martin?
Yes, sir.
Okay. Just wait. Okay. Now, please take the screenshot.
Sir, did you
Mm-hmm.
did any sample papers for physics?
No, we have not completed till now.
Okay.
We will do after this will complete now. Basically, after this lecture, there is a requirement of half an hour to finish this chapter, and this is the last chapter. So after that we will solve. Okay.
Yes, sir.
We will solve the sample papers, we will solve the questions, previous year questions. Because from this chapter, electric motor is related, electric generator is related, Fleming's right hand rule is related, and electromagnetic induction is also deleted. These 4 topics are deleted. So basically you can say 40% of the syllabus is deleted. So we have completed the almost 70% of the board syllabus. 30% is left. I will say 20% is left. So in today's class, I will finish almost 90%, 85% of the syllabus. 15% of the syllabus. For that, there is a requirement of the half an hour class. So maybe I will take your extra class if you want. Means if you are comfortable with that, any other day other than Sunday.
Okay.
Martin, scroll down.
Yeah, yes.
Oh. Okay, take this screenshot, all of you. Monday and Tuesday. Monday, Tuesday. Take a screenshot, all of you. And beta, if you have any doubt, na, then you can ask me. Okay.
Yeah, I took some.
Okay, so okay, now take this screenshot. After this, we are going to solve some of the questions. Martin and Sarah and Hamna, I want to ask you one thing. Are you available on are you available Tuesday at 7:30?
Yes,
Tuesday
sir.
7:30 means I am talking about IST, Indian time.
Um, India is minute.
Martin means
Yes, sir.
Monday, Tuesday. On Tuesday, are you available at 7:30 IST?
Yeah,
7:30 IST. So where are you now?
in UAE.
In UAE. So what is the time there right now?
Sir, that will be 6 a.m.
That will be
6 a.m.
6 a.m. No, 7:30 p.m. IST. I am talking.
7:30 is 5 o'clock.
7:30 is 5 o'clock. Okay, means 2.5 1. So if you guys are available, then I need one extra class because I want to finish this chapter on time. And after that, we will start revision. And revision is very, very important. It means each and every step that you are doing here is important. Okay. Reading, learning, doing questions, and after that, revision. All are important. Attending the class is also important. Okay, now take the screenshot. So completed, Martin and Sarah and Hamna.
Yes, sir.
Martin, please complete.
Yeah, done, sir.
Okay, now take this screenshot. Okay,
Done,
completed. Okay. Martin completed. I think Martin, you are getting some problem na in taking screenshots.
No, I already took, sir.
Then it's fine. Tell me if you are getting any problem. Okay.
Okay.
Okay. Please take this screenshot.
Yeah, done, sir.
Sarah and Hamna, 10.
Yeah, done.
Okay, so please take this screenshot. Now we will solve some of the questions. Then we will have the idea of this theory, how to apply this theory.
Done, sir.
Oh. Okay, wait for 1 minute because it's Azan time, so I will wait for 1 minute.
Yeah, I took, sir. I took.
Okay, now we will solve these 3 questions. The diagram given below represent the magnetic field caused by a current carrying conductor, which is a long straight wire, a circular coil, a solenoid, a short straight wire. Can anyone tell me the answer? These are the magnetic field line due to. Just we have seen just.
Solenoid.
No, not solenoid. You can see I am showing. Okay.
Long wire.
No. This type of na. What you are getting, just I am telling. No problem. See the pattern. Compare the pattern. So compare one straight line, circles. So which is this wire? This wire is, tell me Martin. Circular
Yes.
wire. Circular coil na?
Yes, sir.
So what will the answer? The answer will be circular coil. We are studying theory so that we can solve the problems. Okay. Okay, next question. So removing it. Next question is this. Which of the following correctly describe the magnetic field near a long straight wire? Option 1. The field consists of a straight line perpendicular to the wire. The field consists of a straight line parallel to the wire. The field consists of radial line originating from the wire. The field consists of concentric circle centered on the wire. Can anyone tell me?
D.
Yeah, right. You can see due to the straight wire. Where is the straight wire? This is the straight wire. So due to the straight wire, the magnetic field line or the concentric circle. See Martin and Hamna, you also see.
Yes, sir.
This is the straight wire, and due to the straight wire, the magnetic field line are the concentric circle, and center is lying on the wire. So option D will be correct option.
Okay.
Now third question. Let us now see. The direction of the current in a coil at one end of the electromagnet is clockwise. The end of the electromagnet will be
South.
Yeah. I told you na they here can see. Where is that? If the current is clockwise, okay, if the current is clockwise like this, then it will be south pole like this. And if the current is anti-clockwise, so it will be a north pole. So they are asking for clockwise. They are asking for the current in the means in a coil the current is clockwise. Clockwise means south pole. So these types of question you will get, and some long answers also you can get. Draw the magnetic field line and all that we will do there. Then we will study the electromagnet, and after that we will discuss the solenoid. Almost time left. 5 minutes. Okay, so please take the screenshot of this.
Done.
Done. Matthew, please do this. So tell me if you are free, Martin and Amna and Sarah,
Yes, sir.
on Tuesday at 7:30 IST, or it will be 5 PM according to wherever you are in UAE or anywhere.
Yes, sir.
So I will take in the extra class one more lecture is required to finish the syllabus. Only one. Okay, so Martin took the screenshot.
Done.
Okay, now take this screenshot.
Done.
Okay, do this. Okay, so time is over now. Okay, so we will see. I want one extra class. So if you guys are comfortable, then we can take that class. So when will be your board exams started, Sarah?
From 20th, it will start.
From 23rd
No,
Feb.
20. This Feb, yeah. 20.
23rd Feb. So
Mine's 28.
yours is 28,
No, 20.
20.
First language, so that don't
Okay,
matter.
okay. I can understand that. So what we should do? There's a requirement of one class only, of 1 hour, or it can be a half hour class. So in that class, I will finish the syllabus. And so we should arrange one extra class. Okay, Martin.
Okay.
So on Tuesday, I'm free at 7:30 to 9. So half an hour class will be enough. Okay. And we can finish the syllabus. And after that, if you want the revision, then after that the revision will be started. Okay. Because your exams are very, very near.
Yes, sir.
Your exams are from in Feb or March.
Yeah. First day for the Feb one, it is only small subjects like language, English, and stuff. But from the 4th March, science will be the first one.
Okay. So when will be your science exam?
4th March.
4th March. Okay. And mathematics?
Last 21st.
21st of March.
Yeah.
Okay. Okay, so we will all meet in the next class, and definitely I have to